So, welcome back, class. Hope everybody had a nice, fun Memorial Day weekend. Enjoyed the weather yesterday. It was great. So, just picking up here with the Chapter 11 review sheet that's posted for today. I'll be able to go through specific questions on this also in the Zoom class later. And I'll also have another worksheet for the Zoom class as well with similar types of problems. But this generally hits on most of the topics that you'll see in Chapter 11. We'll have another Chapter 11 review sheet towards the end of the week, also on Thursday, before our assessment on Friday. All right, so just picking up here. Remember, this is considered standard form. It's a rational function because you have a fractional format with a polynomial function on top and a polynomial function on bottom. So that's a rational function. So it's helpful to look at that rational function in two different formats. Standard format is good to assess some of these things. And if you notice, I pre-color coded these the way that I've been doing previous worksheets. So they're the same color codings. So besides standard form, it's helpful to look at this in factored form as well. So if we factor the top, it factors out into x minus 6, x plus 1. And on the bottom, it factors into a difference of squares, x minus 1, x plus 1. So a couple things to note about this that we've talked about previously. We could go in order and all that and go through some of these things. But at the beginning, if you notice, it's very helpful to look in factored form. If you ever notice that there are similar factors on the top and the bottom of a rational function, so right there, that highlighted box right there, they are the same factor. So technically, those factors kind of cancel out. That's called a point of removable discontinuity. You can remove that discontinuity, and then find where that hole would be. So anytime you've got that factor that is a shared factor top and bottom, and you can cancel it out, that's going to be a hole. So letter E, find the point of removable discontinuity. That's that hole. And we know it's going to occur at x equals negative 1. I know that because the factor is x plus 1, so the x value for that factor is negative 1. So we're going to wait on that for a little bit, and we'll get to that towards the end about how to find the y value. But what that does in the effect of the overall rational function is it affects the x-intercepts and the vertical asymptotes, because what would normally appear as two vertical asymptotes and two x-intercepts, now, because that removable discontinuity, it's not either one of those, actually, it's a hole. So you don't have an x-intercept at negative 1, and you don't have a vertical asymptote also at negative 1. So now we can go through kind of quickly through these and say, all right, well, the horizontal asymptote, if you remember, that comes from the leading term. So standard form is easier to identify that. So if I start labeling these things, here's letter A. We're going to get the leading term over the leading term. So that's going to turn out to be just y equals 1. There's your horizontal asymptote. So the graph is going to approach 1 as x goes to infinity and also towards negative infinity. So it's going to level off at y equals 1. We move on to the vertical asymptotes. And you want to do that in factored form, but because this is not considered a vertical asymptote since it's a hole, we only have the one vertical asymptote there. So that's going to be created by that. And what we get there, so for letter B, we have x is equal to positive 1. That's the vertical line for the vertical asymptote. So if you graph this function out, you'll notice there'll only be one vertical asymptote there. Then we go on to the x-intercepts. And again, factored form normally would look like 2 with 2 factors, but one of those is the whole, not an x-intercept. So only one x-intercept remains after we move that discontinuity. So for part C, it's going to turn out to be x equals 6, or you can write 6, 0. So that's your x-intercept. And then the y-intercept, the last one down there, that's in standard form is easiest, or you could just plug in 0 for x and work it out that way. And so in that case, we see that y is going to equal negative 6 over negative 1, or just positive 6. So that means it's 0, 6. All right, so we get down to how do we calculate where this hole is going to be? So we want to plug in negative 1. You can't plug it into the original function or the fully factored function because it will create an undefined value. So what we do is we remove the discontinuity by canceling out the factor and just plug in the negative 1 value from the factor you're removing and plug it into the remaining equation. So we get y equals negative 1 minus 6 over negative 1 minus 1. That's going to be negative 7 over negative 2, or just 7 halves. So when x is equal to -1, y comes out to be 7/2. So here's your point of removable discontinuity. It's going to turn out to be -1, 7/2. Okay? And again, you can verify all that information. If you were to just plug this into y1 and graph it out, you'll see all the same stuff. All right, so now we go on to question number 2. If x minus 1 is a factor of this, what do we know about that? Well, if x minus 1 is a factor, then we know f of 1, when you plug x equals 1 in, it comes out to be 0, because if it's a factor, the remainder would be 0. So we can use this concept by plugging 1 into the expression and setting it equal to 0. That will help us solve for the missing k value. So if we do that, we get 1 cubed minus k times 1 squared, and then plus 2 times 1. All of that set equal to 0, because when you plug 1 in, you're supposed to get 0, which is the remainder, since it's factorable. So we get 1 minus k, and then plus 2 is equal to 0. So this is 3 minus k is equal to 0. If we add the k over, you get k is equal to 3. So therefore, choice 3. And if you plug that in, x cubed minus 3x squared plus 2x, if you set that equal to 0, you'll see x minus 1 turns out to be a factor. So I'll just do this as a check. You don't have to check this, but this is just to show you what it would look like. You take a GCF factor out, you're left with this. And then you can factor down that trinomial. It's going to turn out to be x minus 2 and x minus 1. And so therefore, you can see that that is a factor. So it's factorable. All right. Moving on down, we got the graph. Okay, so how do we write the equation of this polynomial function? So a couple of things we can identify. I see right here there's a root at -3, but this looks like a triple root because of the behavior. So that's going to be one of those triple roots. So the factor at x equals -3, the factor of x plus 3 is going to have to be cubed since it flattens out at that point. We also have another root here at -1. So this one, since it goes straight through, I'll put a little arrow here. Since this one goes straight through, this is really just a single root. So we're only going to have one factor, one power of that factor. This is going to be an x plus 1 factor since x equals -1. And then we have another root over here at +2. And this is bouncing off. So therefore, it's going to be what we call a double root, or any even-powered root, but we're looking for the simplest one. So a double root. And so therefore, this is going to be x minus 2, and it's squared. So I've got those sets of factors. When we write out that equation, let me do this over here, we'll get an expression that starts out y equals a. There's some coefficient. And by the way, we know the coefficient has to be negative because it's going down at both ends. And we know the degree of this has to be some even degree since it's going in the same direction on both sides. So if we look at this, we have a factor of x plus 3 cubed. That's 3 roots, so that's a third degree so far. This is a single root, so that's going to be an x plus 1. And then this is a double root, so this is going to be an x minus 2 squared. 3, 4, 5, 6. This is a 6-degree polynomial, which makes sense. It's even degree. So the only thing we're missing is what's this a value, that unique a value that makes this graph appear where it is. So we could use the y-intercept. We could use 1, -8. We don't want to use the x-intercepts, obviously. We could use a lot of these coordinate points, but the easiest one to use really would probably be the two simplest integer points. So we're going to plug in 1 for x and -8 for y, and we're going to solve. So a times 1 plus 3 cubed, 1 plus 1, and 1 minus 2 squared. So when we work all that out, that comes out to be a, and then times 4 cubed times 2, and times -1 squared. So -8 is going to equal a times, we multiply all this out, and this comes out to be 128. So solving for a, we get 128 divided by on both sides, and a comes out to be -8 over 128, but that reduces down to just -1 over 16. It's negative, which makes sense, the leading coefficient negative, because it's going down to the right. If it was going up to the right, it would be a positive. So we substitute that value back in, and we get -1/16 times x plus 3 to an odd degree. We'll use 3 as the simplest. X plus 1 to a single degree, and x minus 2 to an even degree, but we'll use the simplest for squares. And that would be a typical equation for that polynomial. Okay. Moving on to the back page. All right. So here we have the question about how do we solve polynomials algebraically. So we're going to utilize the synthetic division process. We're going to use our calculator at first, because if you go to try to factor it out by grouping, you'll notice it doesn't work by grouping. So to get around that, how do we still solve this algebraically? You might remember from about a week or two ago, I have the equation in there. I'm going to hit zoom standard. So you're going to see a picture of the graph. What I'm looking for is I'm trying to identify an integer root that I can use to synthetically divide. So I see here that -3 is an X-intercept. So if I go to the table of values, there's an X-intercept at -3. So what I'm going to do is I'm going to use the fact that I know X is equal to -3 is one of the roots, and I'm going to synthetically divide that out. So I'm going to check my coefficients. 3rd degree, 2nd degree, 1st degree, 0 degree. I'm not missing any powers, so I don't need any 0 placeholders. So this is going to be a 2, a -5. It's going to be a -28, and it's going to be a +15. And I know when I divide this out, this last term, it better be a 0, because it should be a root where the remainder comes out to be 0. So if I add straight down, I get 2, multiply diagonal, I get -6. Add straight down, you get -11. Multiply diagonally, you get +33. Add straight down, you get 5. Multiply diagonally, you get -15. And sure enough, that checks out. So I have my coefficients. What this means basically is these are your coefficients of the polynomial 1 degree less, since I just divided out a degree. So this is 2x squared minus 11x and then plus 5. Now what I want to do with that is I want to solve the remaining roots. So you have some options here. I'm going to set this equal to 0. I'm going to try to solve that. I could continue trying to find more rational roots on a calculator and synthetically divide them out. But because I'm down to a 2nd degree, we have other options. We could try to factor it. There's no guarantee that it will factor. Or we could use a quadratic formula or completing the square. I think the quadratic formula probably is the easiest. But it does turn out that this is factorable. So if you wanted to try to factor it out, you could. I'm just going to write out the factors that you would break down if you did it by grouping and did the bridge technique and multiplied the coefficients at the end. So this is 2x minus 1 times x minus 5. So that does factor out, and you'll get these two factors set equal to 0. 2x minus 1 is equal to 0, so x is equal to 1/2, and x minus 5 is equal to 0, so x is equal to 5. So what we have is 1, 2, 3, and they're all rational roots. So your solution set would be -3, 1/2, and 5. There's your solution set to the roots. You could verify all this on the calculator as well, like I was saying. Here's your -3 root. Here's your 1/2 root that you wouldn't see on the table of values unless you changed your delta table to go up by 0.5 steps. And then if I scroll down, you'll see at +5, there's the other root right there. So everything does check out. However, if the remaining quadratic was not factorable, you could still use the quadratic formula to obtain irrational roots or even complex imaginary roots. All right. Next one, number 5, is an inverse variation. So a lot of times I'll have students just highlight that it's inversely proportional. So that's not your typical x over y equals x over y. It's actually the inverse of that. So this is going to be x times the y value is equal to your second pair of values as a product. So they're going to give you information in the problem. This one is pressure versus volume in pounds. So, pressure in pounds versus volume in cubic inches. So you can make either term, whichever one you want. I'll make the first number the x. So 35 times 120 is going to equal the product of the others. This one is asking for the second x value, but they give you the second y value. So basically we get something that looks like this. This turns out to be a product of 4,200. It's equal to 140 times x2. You can divide by 140, divide by 140, and we find out that that second x value turns out in this case to be 30. So what that means is if it's 35 pounds, the volume is 120 cubic inches. If it's 30 pounds, then you end up going up to 140 cubic inches in volume. It's inversely proportional. As this goes down, the other goes up. All right, and then the last one is another rational function, but they're asking you to construct the equation based on information. So I went ahead and I highlighted the different pieces of information with the appropriate colors. So as I go through, I'm going to construct this rational function. Remember, they always have a coefficient a, just like polynomials do. We're going to determine what that a value actually is. So if you remember, the numerator factors come from the x-intercepts. So I'm going to write those in green. Here are my two x-intercepts. I have 1 and -1, which means x minus 1, that comes from a positive 1 root, and x plus 1, that's for the -1 root. Right, those are my two factors. It doesn't mention anything about holes in here, or points of removable discontinuity. So there's no factors that should line up and cancel out. The vertical asymptotes are my denominator factors. So this has 1 at x equals -3, which means x plus 3 is going to be a factor, and 4, so x minus 4 is a factor. Okay, so now we have some other information here. It's got a horizontal asymptote of 1. So when I take the leading term over the leading term, y equals a times x, that's ax squared, and over x times x, that's going to be x squared. So technically, y equals a times x over x times x. This is ax squared over x squared. So these are going to cancel, but it says it's supposed to be 1. So it looks like a should be a 1. So you can figure out the fact that the coefficient has to be just a positive 1 that way. You can also use the information with the y-intercept. And I could take this equation right here, and I can plug in x equals 0 and y equals 1/12. So if I plug in a 0, so let's do it this way, 1/12 equals a times 0 minus 1 and 0 plus 1 over 0 plus 3 and 0 minus 4. So 1/12 is equal to a times -1 over -12. And so in that case, this is like 1/12 equals a times 1/12. If I divide by that, I also come up with the fact that a is 1. So whether you use the horizontal asymptote, so therefore a would be 1, in either case, you'll see that you get the same result. Okay, so the a coefficient has to be 1. So when I rewrite my final answer in this case, where it says write the equation, it's going to say y equals 1 times x minus 1 times x plus 1 over x plus 3 times x minus 4. There's your final equation that would match all of that information. You could go ahead and graph that in y1, and you'll notice that in your picture, you should see at -3. So if we put a little, here's going to be at -3 and at +4. Those are your two vertical asymptotes. I'm going to have a horizontal asymptote at 1. So if I do dotted line across there, I'm setting up the boundaries at that point. I know that at +1, there's going to be an x-intercept, and at -1, there's going to be an x-intercept. So I got that there. And I know that my y-intercept, I'm going to put it down here, it's 1/12, so it's below 1. It's very tight right there. And so my picture, if you were to graph it out, it would kind of look like this. It's going to bend down towards that x-intercept. It's going to go through this x-intercept. It's going to bend down towards that vertical asymptote. And then up here, you're not going to have any x-intercepts. It's going to rely on or exist entirely above the horizontal asymptote at both ends. So your picture would look like that. It would verify all this information as you go through, but that would be your final equation for that one. All right. Later today at the Zoom session, I'll be able to go through a lot of these and review any questions with you, and I'll have another class worksheet for the Zoom session, and then Friday we'll have more time to review. Thursday we'll have more time to review before our online assessment on Friday. All right. Thanks for stopping by.